Hello everyone. Myself, I am Faaiz. I'm from AIIMS Nagpur. Today our chapter is atoms. Okay. From modern physics, our chapter is atoms. So we will see important concepts, important equations, and important theories. Okay. Within like 10 to 15 minutes, and we will solve problems. The first concept we have to discuss is alpha particle scattering experiment. Right. Everyone must have read about this still. Yeah. What did he do? Yeah, he scattered radioactive alpha particles. Okay, from a radioactive. So alpha particles scattered. This is actually, yeah. So most of the main postulates were the most of the alpha particles. Yes, most of the alpha went undeviated, right? And 1 in 8,000 deviate with theta greater than 90 degree, and 1 in 20,000 deviate with theta equal to 180 degree. That is 1 in 20,000 returned back. Okay, 1 in 20,000 returned back. Okay, and for numerical, that's our purpose, main purpose. Okay, first closest approach distance. Second one is number of alpha particles scattered at an angle, its relation, and third one is impact parameter. Okay, first, what is closest approach distance? The closest approach distance is, let me see, the closest approach distance is, okay, now alpha particle velocity. So alpha particle is having a kinetic energy, and here we have nucleus of gold. So alpha particles, okay, alpha particles at a particular point, alpha particle stops. The distance from nucleus to the point where alpha particle stops, that is called closest approach distance. This is the closest distance an alpha particle can approach. Okay, so here potential energy will be maximum, and here kinetic energy will be maximum. Okay, so by solving this, kinetic energy will be, yeah, kinetic energy of alpha particle, which is equal to potential energy will be how much? K q1, charge of alpha particle, charge of nucleus divided by d. From these, we will get closest approach distance will be d equal to, yeah, the closest approach distance d minimum equal to kq1 q2 divided by kinetic energy of the alpha particle. Okay, easy. Yeah. The next one is impact parameter. What is impact parameter and its relation with the theta? Its relation with impact parameter is directly proportional to right, means, see, suppose, okay, nucleus, okay, this is the nucleus. So show 3 alpha particles. This is first one, okay, and this is second one, and this is third one. So this distance is called impact parameter b. So if the distance from nucleus is more, the deviation will be less because there is no repulsion, right? So that impact parameter is directly proportional to cot theta by 2. For numericals, we have to memorize this. And the third one is, yeah, the number of alpha particles scattered, that is n, at an angle theta. Number of alpha particles scattered, n, is directly proportional to 1 by sine theta by 2 always, or sine raised to 4 theta by 2. Okay, easy. So impact parameter directly proportional to cot theta by 2, and number of alpha particles scattered at an angle theta, n theta, inversely proportional to sine raised to 4 theta by 2. Okay, simple. These are the 3 parameters for numericals from alpha particles scattering experiment. Okay, Yeah. Next we have Bohr model. Okay, Bohr model. Bohr model is in orbits are stationary, blah blah blah. Okay, so let's see what's important for numericals for problem solving. The first one is yes, yeah. The angular momentum is quantity of each orbit is constant. Angular momentum MVR, that MVR equal to n into h by 2 pi. Okay, MVR equal to nh by 2 pi, whereas is Planck's constant, it is equal to 6.6 into 10 raised to minus 34, 10 raised to minus 34 joule second. Okay. And the second postulate is every orbit has a fixed energy. Okay, we will come to energy when we will discuss energy levels. So before that, first one is angular momentum is quantized, no doubt. Okay, that is MVR equal to NH by 2 pi. MVR equal to NH by 2 pi. Okay, and so this is nucleus. Okay, this is electron revolving around the nucleus. This electron revolving around the nucleus. So there will be a force, right? That force will be how much? That force will be A charge of electron, charge of nucleus divided by radius of the orbit. So we can equate with electron is circulating in a circular motion. Electron is having a circular motion square by r, and we postulate yes angular momentum is quantized mvr equal to nh by 2 pi. From these equations, when we solve these equations, we will get an equation for radius and equation for velocity. Okay, I'm not getting into those derivations, so simply let me write those equations. The first one is that very important, radius equal to 0.529 angstrom n square by z. This is the first equation for radius. Okay, if anyone want a complete equation, r equal to epsilon naught h square divided by pi m e square n square by z. This is a complete equation. Still r is equal to 0.529 angstrom n square by z. Okay. Next is for velocity. For velocity with which electron is revolving around the nucleus equal to 2.18 into 10 raised to 6 meter per second z by n. Okay. If anyone want complete equation, this equal to this equal to e square divided by z epsilon naught h z by n. Okay. So this is very important, very important. Radius equal to 0.529 n square by z angstrom. Velocity equal to 2.18 into 10 raised to 6 meter per second z by n. Okay. The first part is compulsory. Compulsory. Okay. Easy. Okay. And we have a second postulate, every orbit has a fixed energy. Every orbit has a fixed energy. From that, we can say, suppose, see, if electron energy level to low energy level, this is high energy level, this is low energy level. Yeah, electron will imitate photon. Okay, and this energy gap will be energy gap is equal to, we can say, yes, energy, yes, high energy minus low energy, easy. Can also equate this with hc by lambda. Okay, easy. From that we will get the wavelength of photon. Okay, easy. Okay. Next, yeah, let's discuss about energy levels. Energy levels. For that, we know that kinetic energy equal to half mv square. Okay. So if we derive, okay, putting values for v, we will get an equation k z e square divided by 2r. which is plus kz square by 2r. And potential energy will be k q1 q2 by r, that is equal to minus, because electron is minus, nucleus is positive charge, k z e square divided by r. And total energy will be potential energy plus kinetic energy, right? So total energy will be, if we add this, we will get minus kz e square divided by 2r. Easy. So kinetic energy equal to plus kz square by 2r. Potential energy is equal to minus kz square by r. Total energy is equal to minus kz square by 2r. So we are getting a relation here. What is the relation? Yeah, the relation is very important. Very important. Total energy, which is minus of kinetic energy, which is half of potential energy. No, no. See, this is the okay. Total energy equal to minus k equal to p. Okay. Next equation for total energy is total energy equal to minus 13.6 electron volt. This is the important main equation for total energy. Minus 13.6 z square by n square electron volt. So we get total energy is z square by n square. Okay. Now here, this 13 electron volt is actually Rydberg constant, right? So we have question total energy equal to total energy equal to minus Rydberg constant z square by n square electron volt. Okay, where RC Rydberg constant is 13.6 electron volt. Okay, R into HC. And value of Rydberg constant is 1.097 into 10 raised to 7 meter inverse. Okay, easy. Yeah. So suppose, okay, some electron jumps from high energy level to low energy level. So the energy gap will be high energy minus, okay, low energy, which is equal to Hc by lambda. Okay, so energy, we know the formula minus 13.6 z square by n square. So we can write minus 13.6 z square by n high, okay, square, minus of minus 13.6 z square by n low square, which is equal to Hc by lambda. So we got an equation for 1 by lambda. 1 by lambda equal to rz square into 1 by nl square minus 1 by h square. Okay, this is the main equation. And 1 by r is equal to 912 angstrom. Okay, easy. Yes. And next is hydrogen spectrum. Okay, hydrogen spectrum is simple. What? Okay, excited state is unstable, hence electron returns to its ground state in about in 10 raised to minus 8 seconds. The excess of energy is now radiated in the form of radiations of different wavelength. The different wavelength constitute a special series which are characteristic of atom emitting, and the wavelength of different members of series can be found from the following relations. This is the main relation, okay. The AIIMS series is N1 is 1, N2 is 2, 3, etc., etc. And Balmer is N1 is 2, N2 is 3, 4, 5, etc. And Paschen series N1 is 3 and bar bracket N1 4. Okay. P fund N1 5. Okay. Easy. We have to by heart energy levels of hydrogen and helium plus. that is must. So for hydrogen, okay, ground level n equal to 2, n equal to 3, and okay. For helium also we have to by heart. Yes. This is for helium. This is for hydrogen. Hydrogen n equal to 1, energy is minus 13.6 eV, and n equal to 2 minus 3.4 eV, n equal to 3 minus 1.51 eV, n equal to 4 minus 0.85 electron volt. Okay. Helium minus 54.4 electron volt, minus 13.6 electron volt, minus 6.03 electron volt, minus 3.4 electron volt. And we have to study the energy gaps also. Energy gaps in hydrogen atom. Energy gaps in hydrogen atom. Between 1 and 2 will be 10.2 electron volt. Between n equal to 1 and 3 will be 12.09 electron volt. Between 1 and 4 is between 1 and 4 is between 1 and 2, between 1 and 2 10.2, between 1 and 3 12.09, between 1 and 4 12.75 electron volt. In helium, between 1 and 2 is 40.8 electron volt. Okay. Easy. Yes. And Lyman is Lyman 1, Balmer 2, Passion 3, bracket 4, P fund 5. And in Lyman, we have first line, we have last line, and we have series limit. First line means yeah, 2 to 1. Last line means infinity to 1. And series limit means also infinity to 1. First line have low energy gap. Low energy gap means longest wavelength. Longest wavelength. And last line will have shortest wavelength. Easy. Yes. So yeah, let's start problem solving. This is our first question. In the line spectra of hydrogen atom, difference between the largest of the Lyman series. That means difference between first line and infinite last line. The Lyman series is given 304 angstrom. I have to find out the corresponding Paschen series. So Paschen series means n equal to n1 equal to 3, right? n1 equal to 3 for Paschen series. Yeah. For Paschen, n1 equal to 3. So first line will have a low energy gap. So low energy gap means largest wavelength. First line, largest wavelength, which is equal to 4 to 3. And last line means shortest wavelength, which is actually infinity to 3. Okay, easy. Yeah. We have to find out the energy difference between largest and shortest wavelengths of the Lyman series. Okay. Yeah. So see, what's the formula? 1 by lambda equal to, okay, 1 by lambda equal to rz square into 1 by nl square minus nh square. Okay, that's our formula. So 1 by lambda equal to rz square into 1 by n square minus nh square. So for first line, lambda 1, for first line, 1 by 9 minus 1 by 16, right, is equal to rz square into 16 minus 9, 7 divided by 16 into 9, 144, right, 90, 54, yes. So lambda 1 will be how much? 144 divided by 7 z square into 1 by r. Okay, yes. We know that value of 1 by r is, okay, value of 1 by r is, we know value of 1 by r is, yes, 912 angstrom. And last line, for last line, 1 by lambda l rz square into, okay, this is for hydrogen atoms, so z is equal to 1. 1 by low nl square, that is 9 only. 1 by infinite square, 0. So 1 by 9. So this will be, so from this, lambda L will be how much? Lambda L will be 9 by z square into 1 by r. Z square equal to 1. So we have to find difference between lambda L minus lambda 1. Okay. Lambda 1 minus lambda L. Okay. For that, so we will get 1 by r into 144 by 7 minus 9, right? So 1 by r into 144 minus 9 into 7, 63 divided by 7. This will be how much? 1 by r is 9 2 angstrom into 144 minus 63. 44, 6, 19, 19. So 81, 81 by 7. So this will be 912 into 81 by 7. Okay. From this we will get the answer. Okay. Easy. Yes. Let's move on to next question. This is our next question. A particle of mass is given 200 mega electron volt per c square. So E is equal to mc square. From this we can write as unit of mass as E by c square. That is energy by c square. Mega electron volt by rest. Soon after the collision, the particle comes to rest and the atom recoils and goes to its first excited state. Initial kinetic energy of the particle in electron volt is n by 4. The value of n is given the mass of the hydrogen atom is 1 giga electron volt by c square. So now the condition is like this, right? Initially, it is at moving with velocity v0 and it is at rest. Okay. Hydrogen atom is at rest. And just after collision, this particle comes to rest and hydrogen atom is moving with velocity v1. So by conserving momentum, we can conserve like mv naught equal to mv1. So v1 will be small m by capital M into v0. Okay, easy. Process, there will be a loss of kinetic energy. That kinetic energy is going as an excitation energy for the hydrogen atom, for the electron in the hydrogen atom. So we can say that the loss in kinetic energy during collision is actually what? Here, Yeah, here excitation energy. So loss in kinetic energy will be kinetic energy initial, kinetic energy initial minus kinetic energy final. Okay, that will be the loss, not change, loss. This will be half m v naught square minus half capital M into v1 square. So for v1 square, if we substitute small m by capital M into, so small m by capital M v0 square m square. Okay, so we will get half m v naught square. We can take common 1 minus small m by capital M. Okay, this will be the excitation energy. This will be the excitation energy. It is given that atoms requires and goes it's to first excited state. So first excited state, what is the excitation energy to required to go to first excited state, that is n equal to 2 in hydrogen. We have energy levels. Yeah, so 13 point minus 13.62 minus 3.4, that's between 1 and 2. Energy gap is 10.2 electron volt. So that will be the loss in kinetic energy. So we can write it is equal to 10.2 electron volt. Okay. Next, we have to do small m by capital M. That is mass of the particle by mass of hydrogen. Mass of the particle is given as 200 mega electron volt. 200 mega 10 raised to 6 electron volt per c square divided by mass of hydrogen atom is 1 giga electron volt. 1 giga electron volt. 1 into 10 raised to 9 electron volt per c square. We can cut 10 raised to 3. So 1200, 1 by 5. So small m by capital M is 1 by 5. Okay. And 10.2 electron volt, which is equal to half small m v naught square into 1 minus 1 by 5 is equal to 4 by 5. Actually, what is this? Half m v naught square initial kinetic energy. Question it is saying that initial kinetic energy of the particle is n by 4. Initial kinetic energy of the particle is n by 4. So we can write. Okay, so initial kinetic energy, we have to find out initial kinetic energy only. So we can write 10.2 into 4 by 5, 5 by 4. This will be the initial kinetic energy, which is equal to n by 4. So this is the n. This is the n. That is 5 into 10.2. That is how much? 51. So n is how much? 51. N is how much? N is 51. Okay. Okay. Easy. Okay. This is our next question. In a hydrogen atom, the electron makes a transition from n plus 1th level to the nth level. Okay. If n is very much greater than 1, the frequency of radiation emitted is proportional. The frequency of radiation emitted is proportional. Again, very simple question, right? What's really happening here? Yes, electron jumps from n plus 1th level to n level. Okay, we have to find out the frequency. So we can, so we know the formula. What's formula? 1 by lambda equal to r z square 1 by n square n low minus n high n plus 1 whole square, so which is equal to r z square n plus 1 whole square minus n square divided by n square into n plus 1 whole square. Okay, easy. Now, okay, 1 by lambda, see here 1 by lambda, multiplying c both side, c by lambda. What is c by lambda? C by lambda is frequency, right? C by lambda is frequency. So frequency will be CRZ square. Okay, n plus 1 whole square minus n square. That is n square plus 1 square plus 2ab, 2n minus n square divided by n square into n plus 1 whole square. Okay, this will be, frequency will be, we can write CR z square. Okay, and we can cut 1 plus 2n divided by n square into n plus 1 whole square. Question it is given that n is very much greater than 1. So n is very much greater than 1. So n plus 1 we can write as n, and 1 plus 2n also we can write as 2n. So frequency will be CRZ square 2n divided by n square into n square, that is CRZ square into 2 divided by n cube. So the proportionality will be, frequency is inversely proportional to n raised to 3, or frequency is directly proportional to n raised to minus 3. So which option is the correct option? 1 by n cube. B is the correct option. 1 by n cube. Okay. Let's solve next question. This is our next question. The time period of revolution of electron, time period is given in the ground state. Ground state means n equal to 1. Is 1.6 into 10 raised to minus 16 second. The frequency of revolution of the electron in its first excited state. So n equal to 2. We have to find out the frequency where n equal to 2. Okay. We have already radius velocity equation. Where is that? Yeah. Radius velocity. Where? Yeah. Radius proportional to n square by z. Velocity proportional to z by n. Okay. From that. So we know that radius is proportional to n square by z. Velocity proportional to z by n. What will be the time period? Time period will be distance upon speed, right? Well, here distance is 2 pi r velocity by v. So the time period will be proportional to n square by z by n. So we got a proportionality for time period. Time period is proportional to n cube divided by z square. N cube divided by z square. So here I have to find out frequency at n equal to 2. Frequency at n equal to 2. So time period at n equal to 2 will be how much? Yeah, time period at n equal to 2 will be n equal to 2 will be. So t proportional to 2n cube, right? So t proportional to 8 n cube. So time period will become 8 times, right? Time period becomes 8 times. Time period becomes 8 times. So new time period t dash will be 8 into, we have already given the first time period, because at n equal to 1 time period, 1.6 into 10 raised to minus 16. 1.6 into 10 raised to minus 16. We have to find out frequency will be 1 by 8 into 1.6. Will be 10 raised to plus 16, right? You can solve like 100 by 8 into 1.6. 8, 4.8, like 12 point something, 12.4 something, 10 raised to 14. So this will be 12, 25, 4, 8, something like approx 8 into 10 raised to 14. Approx 8 into 10 raised to 14. So yeah, so our answer will be option B, 7.8 into 10 raised to 14. Okay, easy. Next. Moving to next question. Consider an electron in a hydrogen atom revolving in its second excited state having radius is given. The de Broglie wavelength of this electron is de Broglie wavelength. What is the equation for de Broglie wavelength? The equation for de Broglie wavelength is lambda equal to h upon mv. For v, we can solve like 2.18 into 10 raised to 6 z by n meter per second, like this. And we know from this we can solve that Broglie wavelength. But we have another thing. What is that? See, we know that at n equal, okay, at n equal to, see, at nth orbit, electrons are making wave, right? The number of waves will be, number of waves will be, and number of waves will be n. That means here it is saying that revolving in its second excited state. Second excited state means n equal to 3. At n equal to 3, at n equal to 3, at n equal to 3, n equal to 3, 1, 2, 1, 2, 1, 2. Yeah. Electron will make, electron will make three waves. So three waves. So we can say that, so this one wave is actually lambda, right? Wavelength will be lambda. So we can equate that 2 pi r equal to 3 lambda at n equal to 3. If n equal to 2, 2 pi r equal to 2 lambda, right? So from this, we will get what? Lambda, the wavelength lambda equal to 2 pi r divided by 3. 2 pi divided by 3. Question it is given 2 into 3.14. R is given how much? R is given 4.65 angstrom. 4.65 divided by 3. Answer will be, yeah, we can cut this, making approx 2 into 4.6, like approx 9. Approx 9, right? Approx 9. So 9 point something will be in angstrom, the answer. So which option? Yeah, option D will be the correct answer. Okay. So at nth orbit, the number of waves will be n, right? Yeah. This is our next question. In lithium 2 plus, electron in first Bohr orbit is excited to a level. First Bohr orbit is excited to a level at n equal to 1, to a level by a radiation of wavelength lambda. Okay. When the ion gets de-excited to the ground state in all possible ways, including intermediate emissions, total of 6 spectral lines. How many spectral lines? 6 spectral lines. What is the value of lambda? We know that, yes, if the electron is de-excited from n to first Bohr, first orbit, n equal to n to 1, possible number of spectral line, possible number of spectral lines, possible number of spectral lines will be equal to how much? N into n minus 1 divided by 2. This is the equation we have to, we had this possible number of spectral lines is equal to n into n minus 1 by 2. This is the possible number of spectral lines. Okay. And here it is given that, in question it is given that spectral lines are 6. So n into n minus 1 by 2 is 6. That is n into n minus 1 is 12. So if we give n equal to 4, then 4 into 3, 12. So n is 4. So actually, yeah, this is the condition. From 4 to 1, yeah, electron got de-excited. So we have to find out the wavelength, right? What is the wavelength? What is the value of lambda? We have equation. What is our equation? 1 by lambda equal to r z square into 1 by n l square minus 1 by n h square. N l square is 1 only. 1 square by 1 by 4 square is equal to r z square into 1 minus 1 by 16. 1 minus 1 by 16. And it is actually lithium, right? It is lithium, Li2 plus. So Z is equal to 3. So R into 3 square, 9. 16 minus 1, 15 divided by 16. So our lambda will be how much? 16 divided by 15 into 9 into 1 by R. 1 by R we can write 912 angstrom. 16 divided by 15 into 9, 912 angstrom. So this will be approx how much? And in nanometer. Okay. So 10 raised to minus and 10 raised to minus 9. This will be approx Mm, 912, yes. So, 35 nanometer, right? Okay, I am cutting this 16 and 15, okay. So, 1 by 9. 1 by 9 into 912 into 10 raised to minus 1 meter. 1 by 9 into 900 around 9. No, no, I can't do that. 912. 912 by 9. 912 by 9 will be 9 will be above 6, about 10, about 10 nanometer. This will be the answer. About something nanometer. But it won't be 9 times, 11 times. 11 into 9, it will be 11 into 90. How much? 990. So it won't reach there. So option will be D only. Yes. Next question. The radiation coming from transition n equal to 2 to n equal to 1 of hydrogen atoms fall on helium plus ions in n equal to 1 and n equal to 2 states. The possible transition of helium ions as they absorb energy from the radiation. Very simple, right? From hydrogen atom, what's happening? Yeah, from hydrogen atom happening is n equal to 2 to n equal to 1. So the emitted radiation will have energy of 10.2 electron. That's why we have to behind that 10.2 electron volt. And we helium plus energy levels. Helium plus energy levels is 54.4, 30.6, 6.03, and 3.4. So at 3.4 to 13.6 level, the energy gap is 10.2. So this is n equal to 2, this is n equal to 4. So for helium, the answer will be n equal to 2 to n equal to 4. Easy. Yeah. This is our next question. According to Bohr's theory, the time averaged magnetic field at the center of a hydrogen atom due to the motion of electrons in the nth orbit is proportional to. Yes. What is the formula of magnetic field? Magnetic field formula is B equal to, due to circular ring, formula is mu naught I divided by 2R. And actually I proportional to Z square by N cube. Okay, I proportional to B proportional to B proportional to N square by Z. Z cube by N raised to 5. So be proportional to Z cube by N raised to 5. Z cube by N raised to 5. So answer will be N raised to 5. Next question. One were to apply Bohr's model to a particle of mass M and charge Q moving in a plane under the influence of the charged particles, and the nth level will be the centripetal force, that is F is equal to, yeah, here the centripetal force, that is F equal to who is providing that? Yes, QVB, because magnetic field existing there. So MV square BR. And we know that yes, angular momentum is quantized. Right. From this we will get equation for R. R equal to MV by QB. I'm applying here R. So this will be MV into MV by QB, which is equal to NH by 2 pi. So this will be how much? MV square. MV square. NH QB divided by 2 pi multiplying with half. This is kinetic energy. Kinetic energy K equal to 1 by 4 NH QB by pi M. So energy will be how much? 1 by 4. 1 by 4. 1 by 4 NH QB by pi M. NH QB by pi M. Yes. Which option? Yeah. Option C is the correct option. Okay. Moving to next question. A photon is emitted in transition from, this is latest question, right? 2022. From n equal to 4 to n equal to corresponding wavelength of this transition is again hydrogen n equal to 4 to n equal to 1, n equal to 4 to n equal to 1, n equal to 4 to n equal to 1, n equal to 4, 1, 2, 3, 4. Okay, the energy gap is between 1 and 4 is. We can solve like this also if you don't remember this. How? How can we solve this? Yes. Can solve like this, no? We have equation what is like HC by lambda will be equal to 1 minus 1 by 16. Right. So in 18.volt, this will be, if we solve this, we will get 91.4 nanometer. Simple calculation only. Okay. So option will be 19, option 1 will be the correct answer. Next, the wavelengths of radiation emitted is lambda naught when an electron jumps from the second excited state to the first excited state of hydrogen atom. The electron jumps from the third excited state to the second orbit of the hydrogen atom. The wavelength of the radiation emitted will be 20 by x lambda naught. The value of x is again similar kind of problems. First is n3 to n equal to 2, right? Second excited state to first excited state, n equal to 3 to n equal to 2. So I can write as lambda equal to r z square. Hydrogen only, so okay. R 9. So this will be how much? R into 9 minus 4, 5 by 36. Right. So lambda will be 36 by 5 into 1 by r. Right. And in second case, okay. This is lambda naught. So lambda dash is from n equal to 4 to n equal to 2. So lambda dash will be how much? 1 by lambda dash will be r into 1 by 4 minus 1 by 16. This will be how much? R into 16 minus 4. 12 upon 4 into 16. 3 by 16. 3 by 16. So lambda dash will be 16 by 3 into 1 by 16 by 3 into 1 by r. Okay. So and it's saying that it is equal to 20 by x lambda naught. Okay. So we will get for 1 by r will be equal to 5 lambda naught divided by 36. Right. So if I equate that, lambda dash equal to 16 by 3 into 1 by r, I can substitute as 5 lambda naught by 36. 20, 36, 18, 9, 4. Okay, this will be 20 lambda naught divided by, so x will be 27. Easy. Similar type of question. The radius of electron's second stationary orbit in Bohr's atom is r. The radius of third orbit will be. Yes. Let me again revise. Yes. What is the formula of radius? Yes. This is formula 0.529 z. That's formula. Right. So radius is proportional to n square by z. Radius is proportional to n square by z. So radius equal to 0.529 angstrom n square by z. The radius of the electron's second stationary orbit. So n equal to 2. So n equal to 2, r is okay. N equal to 2. So r equal to something constant into 4 by z. Right. I have to find out the radius of third orbit will be. Third orbit will be r dash, which is equal to k into 9 by z. I have to find out this r dash in terms of r. Just divide r dash by r will be r dash by r will be kk, we can cut 9 by 2 by 9 by z by 4 by z. Okay. So how much r dash will be? Much 2.25 r. 2.25 r. So which option? Option number two. Option number two will be the correct answer. Option number two will be the correct answer. Okay. We have a last question. An electric atom jumps from fourth energy state to second energy state. Okay. Energy released in this process will be given RCH electron. Again, very simple question, right? How are we going to solve these? Again, let me revise the formula. Yeah. Total energy is equal to minus 13.6 Z square by N square electron volt. So minus 13.6 is R at C. Okay. Question also it's given. Right. And energy gap will be minus 13.6 Z square by N square electron volt. Okay. Let me solve this. Energy released, right? So energy released means I have to find out energy gap. So energy gap will be jumps from fourth energy state to second. So first we have to find out fourth energy and E2. Okay, easy. First E4 will be how much? Minus 13.6 Z square by N square. Z square is 16 by N square. N square is also 16 electron volt. Okay, and E2 will be minus 13.6 divided into Z square by N square. Z square is 14 again, but N square is 2 square, that is 4 electron volt. So this will be minus 13.6 electron volt, and this will be 4 minus 13.6 into 4. 4 into 6, 24. 2 remaining 12, 4, 1, 5. Minus 15.4 minus 54.4 electron volt. So the energy gap will be energy gap or energy released in this process will be E4 minus E2 will be how much? Minus 13.6 electron volt minus 15.4 electron volt. This will be minus 13.6 plus 54.4 electron volt. This will be how much? Yeah, this will be 40.8, right? 40.8 electron volt. 53, okay. 40.8 electron volt. So which option will be the correct answer? Option 4. Let me again, okay, this question number 2. A photon is emitted in transition number 4 to n equal to 1 level in hydrogen. The corresponding wavelength, we know the equation. Yeah. What is 1 by lambda equal to rz square 1 by nl square minus 1 by nh square. R is how much here? Okay, R we know rz square. It is hydrogen only. So z equal to 1. So R into 1 by low 1 square minus 1 by 16. Right. This will be R into 1 minus 1 by 16. And this will be how much? R into 15 by 16. R into 15 by 16. So 1 by lambda is R into 15 by 16. And lambda will be 16 by 15 into 1 by R. You know 1 by R is 16 by 15, 912 angstrom. 912 angstrom. 912 angstrom. Okay. 3 3 and 4 3. Right. 5 3. Okay. And 34 into 16. 4 2 remaining 24 4 3 4 4 5 5 4 4 by 5 will be yeah 94.1 nanometer, and so will be how much? 94.1 nanometer. I have to do unit 10 raised to minus 1 because it is given in angstrom, right? Yes. Yes. And so will be 94.1. Okay. And so will be 94.1. Okay. Thank you everyone. Completed the topic atoms. Okay.